Okay. All right. Hey. Time to stop having fun.
Damn it.
It's time to do physics. Damn it. I'm just kidding. Okay. I apologize for the 5 minutes of our precious time that were lost. Eric didn't realize when he scheduled the special colloquium that there was a class in here. So anyway.
Come on, that's your job.
It's my job. I did. I scheduled this room for 5 o'clock. I just literally kicked half of my colleagues out of the room. No questions. You saw it. You were there. I care that much. Okay, I care that much because today is really cool. Today is probably one of my favorite topics in this entire course, and it's one of the things which. It's one of the things which, when I first saw this, it's kind of what made me fall in love with particle physics. So hopefully you'll derive at least a little bit of that same joy out of this. And if you don't, screw you. Okay, so what we've done so far in looking at equations of motion and Lagrangians and so forth is to basically analyze what we would need in order to describe freely propagating field excitations, also known as particles. And we have, in the course of that development, come up with 3 Lagrangians, one for spin 0, one for spin 1/2, and one for spin 1. The spin 0 Lagrangian, of course, leads to the Klein-Gordon equation and takes this form. We will not be using this so much today, although we will later on in a couple of weeks revisit the Klein-Gordon Lagrangian. What we're really going to be focusing on a lot today is the Dirac Lagrangian, and the reason for that is because what we want to do is talk about the interactions between matter in the standard model, and of course all matter particles in the standard model, as it turns out, are spin 1/2 particles. They're fermions, and so they're going to be described, at least for the free non-interacting case, by the Dirac Lagrangian. And then what we will discover is that in the process of introducing interactions, we're actually going to also need to fold in, even though we don't start out with it, we're going to have to fold in the Procol-Lagrangian. And so all of these various Lagrangians are eventually going to be made use of. Today we'll just really make use of the second 2, and then the first one we'll see a little bit later. Okay, so one thing to note is that the free Lagrangians are all quadratic in the fields or in derivatives of the field. So, you know, d mu phi, phi squared, psi bar psi, d mu psi. This was a little weird. It's a product of a field and a derivative, or it's actually a product of the adjoint field and the derivative of the original field. And then buried in these f mu nu's, since they're built out of dA, this thing is generally going to contain quadratics and derivatives of A. Okay, and then the mass term, of course, is just a product of the fields. Now you might ask, if 2 different fields are interacting, then what might we expect a term in the Lagrangian to look like? So for example, you know, if I had a spinner field and it was interacting with a scalar field, how might that be reflected in the Lagrangian? And it's actually the simplest kind of thing you can imagine. If the Lagrangian had some term that involved just a product of those 2 fields, and there could be some constants that multiply that, possibly imaginary. But if you have a product of these 2 fields, then this is actually going to reflect an interaction between these 2 fields. Okay? So you'll notice in nothing that I've written so far do I have products of different fields. I, of course, have a product of a field with itself, and that is how we interpret the field giving rise to mass. The field excitation sort of itself carries energy. But what we're really interested in today is the interactions between different fields, and so we're going to be on the lookout for terms of this form. Okay? And you could also by the way, have a term like this, where you have a scalar field and then you have a derivative of a spinor field. And that would still be an interaction term because it largely involves two fields kind of multiplied together. The fact that you're multiplying a field times the derivative of another one, that's just a more sophisticated feature of the interaction, but nonetheless, this would be a possible interaction term as well. Okay, so one thing that you might guess is that to create interactions, you could take say two of these, say take the spin a half Lagrangian and the spin one Lagrangian, or the free Lagrangians, add those together, and then just add on any product of fields that you could possibly imagine. You know, so I could just start doing things like this. And then give these a bunch of coefficients. And that would be a way to just kind of generate, you know, a whole mess of interactions. And truthfully, that's really not that sexy, right? If you're just free to put in anything you want, it's not very inspiring. Well, turns out that in a certain sense you can't do this, because one thing we have to make sure of is whatever Lagrangian we end up with, it needs to share the symmetries that we hold valuable in our theory. In particular, it has to be Lorentz invariant. And so, for example, a term like this would not be Lorentz invariant. It's got a mu that's not canceled by being summed over with any other mu in this term. So a term like this we would not write down. A term like this would actually be fine because these two combine to give me a scalar, and then we already know side bar side combines to give me a scalar. So a term like this would be fine. But if you think about it, if you just restricted yourself to Lorentz invariant terms, you could still write down an arbitrary number of interactions. Just more, like you could just take this term and do higher powers of it. Okay? So what you could do is you could write down every possible conceivable interaction, and then you would have before you the very lofty task of comparing the predictions of that Lagrangian to what you observe in experiment. And what you would discover, and what took a long time to be realized, but was eventually settled upon, was that if you took all of these terms, all possible terms, and then compared them to what you see in experiment, it turns out that a large number of the terms are not relevant. You don't actually use them. There's only a very small handful of terms that get used, and the really beautiful part of the result is that the terms that get used and the way that they enter into the Lagrangian is completely dictated by a symmetry principle. And so what we're going to talk about today is how that symmetry principle actually gives rise to the interactions that we observe. And we're going to look at the simplest case today of an abelian interaction, and then next time we'll generalize it to the non-abelian case. Okay. So there's a program, sort of a recipe that we will follow in detail. And I'll just call this recipe for a gauge theory. And bear in mind, all of the fundamental interactions in nature are gauge theories. So this is a very important and powerful conceptual framework. So the first step of this recipe, and I'm going to write this in words, but we're actually going to see it play out in a concrete example with the math, is to begin with a free matter, and by matter we of course mean a Dirac field, because all matter is spin half fermions. Begin with a free matter field with a global symmetry. Or a free Dirac, actually I should say a Lagrangian is what I mean. Okay, so a Lagrangian made of freely non-interacting spin and half particles. And then what we're going to do in the next step is we're going to promote the global symmetry to a local one. Okay, and those words might not mean very much to you right now, but we'll see exactly what that means in the course of the example. And what we will find is that this particular step induces interactions. Okay? So by taking the global symmetry that we start out with, where there's no interactions, and forcing it to hold locally, then we end up having to introduce interactions. And then the last step is to allow the new gauge field to propagate. And then step 4 is to go have a beer. Okay. All right.
Go love a beer.
Go.
It's like a love.
Lave.
Well, what's the difference? If you have a beer, you're gonna love a beer. All right. Anyway. Yeah, I know. This is the lecture I should have had for the day before E-Days. That would have had no relevance. Your condition. Okay, so here we go, folks. This is what all of those words mean in one super hardcore but incredibly relevant example. So I'm going to start with the free Dirac Lagrangian. So step 1. Okay. And it turns out that without doing anything else to this Lagrangian, we can already identify a global symmetry. And it really stems from the form of the Lagrangian and the fact that the spinor fields in there are complex. Okay? So one thing we might notice is that if we took the spinor field psi and we transformed it, now this is not a coordinate transformation. We already know how a change of coordinates affects a spinor. We have to build that, the commutator of the gamma matrices and then exponentiate those and create the analog of the Lorentz transformations on spinners. This is a different transformation. It has nothing to do with coordinates. I can literally take that spinor psi and multiply it by a complex number, and I'm going to write the complex number in a very weird way. Okay? Where in this expression, this q is a constant, and just to make it clear, this phi, on the other hand, is also a constant. Okay? You might say, why do you multiply two constants together? Well, in a minute, we're going to change that. But for this starting point, those are just two constants, and we'll identify what they are later on. And recalling that psi bar is defined as I gamma 0 psi dagger. Okay? Actually, I guess in principle, these are transposed. If you want to work it out with matrix multiplication, then you can use this identification, this operation, and you very quickly realize that the transformation rule for psi bar is that psi bar prime just becomes psi bar e to the minus I q phi. Okay? So we start with this definition of the transformation, and because psi is related to psi bar, we can deduce this transformation for psi bar. Okay, so specifying one determines the other. Okay? And then what we notice is that this is a symmetry of this Lagrangian. Let us consider what happens to the Lagrangian if we enact this transformation. So we've got our h bar c, that doesn't change. Psi bar picks up an e to the minus I q phi. Gamma mu d mu. Gamma mu and d mu have nothing to do with the fields. Gamma mu and d mu would change if we were doing a Lorentz transformation. Okay? But they have nothing to do with the fields themselves, and it's the fields I'm transforming. Okay? So they don't get changed. And then, of course, psi gets that e to the I q phi psi. And then the mass term and then we notice, hey, look at this. Boom. That's the identity. And this is just a complex number. Nothing fancy. It's nothing weird in space-time. It's nothing weird in spin space. So there's no reason whatsoever why I couldn't just grab this shoot it to the left of all those terms, and then it combines with the e to the minus iq phi to give me the identity again. And then what I notice at the end of all this is that the Lagrangian just goes back to the original form. Okay? Everybody on board? That seems so almost trivial that you just don't really seem like you could get any meat out of it. And you can't. But now we're going to do something extra special. We are going to, in step 2, promote this to a local transformation. Now what does that mean? Well, what it means is that when I transform psi to psi prime, I want the transformation operator, this e to the iq phi, to actually be allowed to be different at different positions in space-time. Okay? So one way to do that is to take one of these two constants and make it a function of where you are. Okay? And then that will just act on psi. So that's why I introduced two constants, because we're going to promote one of them to a function, and then we're just going to leave the other one as a constant, which will play an important role we'll see in a bit. But now we can go ahead and infer from this how psi bar would transform. And it probably comes as no surprise that that transforms as e to the minus iq phi, which is a function of x mu. Yeah, you gotta, it's a multi-step procedure to get rid of the string. And then you gotta get rid of the green cups, because St. Patrick's Day came and went.
For step 4.
Yeah, that's step 4. It's for step 4. Okay, all right. Now, if you think about it for a moment, the idea of making a transformation local is weird, right? For example, we talk about rotations. So now I'm talking about space-time transformations. We talk about rotations, and when we talk about rotations, we talk about rotating everything uniformly. So if we're doing a rotation by 2 pi around the x-axis, everything transforms by a rotation by 2 pi around the x-axis. Just to give you an idea how weird this is, a local rotation would be where I take stuff over here and rotate it by, pi over 2 around the x-axis, and stuff over here rotate it by pi around the x-axis, and stuff over here rotate it by 3 pi over 2 around the y-axis, and then miraculously everything is unchanged. That's what a theory invariant under local rotations would exhibit. Now that's really weird to wrap your head around, but it's actually possible to create theories like that, and I'll mention one a little bit later on. But for now, this is literally the kind of thing we're trying to do. We're trying to allow ourselves the flexibility of making this transformation different at every different point in space-time. Of course, you do not have to. You could say that this function, phi of x mu, is just a constant. And then, of course, you're just back to doing this global transformation. Okay? So notice the words global and local apply here. And we talked about these when we first started talking about groups and transformations, and we looked at some actual static examples of local and global transformations. And I think we were like rotating circles, and then we were moving around dots. And so you can go back and review those notes. All right? Now, at first sight, it might seem like there's no way in hell that that Lagrangian is going to be invariant under this transformation, and you would in fact be correct. But what is instructive is to study how this Lagrangian fails, because what we're going to then do is fix it. Okay? So let's see what happens to our Lagrangian under this local transformation. So again, I just throw in what I've already determined. Okay. That's exactly what I did up here in the global case. And now what I would like to do is see if there's any cancellations. Of course, we immediately see the cancellation in the mass term. The e to the minus iq phi, the e to the iq phi combined to give me the identity. But here's the problem. And what problem do we notice?
Can't move it past the derivative.
Yeah, we can't take a function and arbitrarily move it past a derivative, like we could a constant. Okay, here we move the constant transformation past the derivative. In fact, if we want to evaluate this, what we should do is evaluate that using the product rule. Okay, it is the derivative of a product of functions. Psi itself is a function of where you are. Okay, so if we do that, then what we unearth is how this thing fails. And so we get an expression of the following form. E to the minus iq phi x mu, gamma mu. If I let the d mu hit the exponential term first, I'm going to pull down a factor of e to the I d mu phi x mu, and I'm going to put that in parentheses to remind us that's the only thing the derivative's acting on, times psi. And then I next let it act on psi and then pull the e to the I out. Okay. And then the last term, of course, just goes back to what it started as. This thing's tidy. Okay. And then if we look carefully, we notice that this term and this term actually do simplify, because with the exponential on the other side of the derivative, it can cancel with this exponential. So we are going to get a term which is just what we started with, but we're going to get this extra piece, okay? And if I grab all my factors and put them together, h bar c q psi bar. Oh, I'm sorry, I failed to take the derivative correctly, and you guys have to call me on that. Sorry. So that's that, and then I get this factor e to the I q phi x mu psi plus e to the I q phi x mu d mu psi plus mc squared psi bar psi. Okay. When you take the derivative of an exponential, you get the derivative of the exponent times the original exponential. Okay, so this, with this term, just gives me back what I started with. And then for this term, now this exponential can cancel this exponential, because this is not being derivated, derived. Derivatized. Okay. So in the balance of this is going to be IQ psi bar gamma mu d mu phi x mu psi. D mu psi. Yeah, there we go. Okay.
Why did that index on the x mu go down?
Oh, yeah, sorry. My apologies. I should be really careful. So if I had been careful, I would have actually called this probably x mu. If this is the argument of phi, so there's no sense in which these two are contracted. So to make it clear, these should be like x nus. They don't tell you anything about how something transforms. The mu here does contract with the mu there, okay? And the mu here contracts with the mu there. So, but yeah, I should have kept it up everywhere, but I failed epically. Okay. MC squared psi bar psi. Okay. So it's this piece here that is sort of screwing things up. And as far as this story is written, there's really nothing that we can do with what we've got to get rid of that piece. Okay? Does everybody agree that if this thing weren't there, I would have just gotten back what I started with? Okay, so the philosophy of making this work is to add something to the story which will essentially cancel this piece off. Okay? Now we're adding something to the story. All right? But the form in which we add it is going to be dictated by wanting to get rid of how this is screwed up. Okay? So what I'm going to do is undo this. Yeah, I'm just going to undo this. We're still going to be considering the same transformation. It's still going to act the same way on the dual spinner. But the modification that we're going to make is we're going to change the derivative. After all, we love physics. Let's beat up on calculus. So to try to fix this, we're going to take the ordinary derivative and replace it with a newer, gooder derivative that we are going to call, by no accident of degeneracy, a covariant derivative. And that new derivative is going to essentially be the old derivative plus some new term, which for now I'm going to call IQ a mu, where this q, I can kind of look ahead, is going to be related to that q, and then we'll identify what this guy is later on. I is just going to be there to get the complex part of everything to work out. And it's important to realize that while q is constant, this a mu is certainly not a constant. It's actually something that can vary from place to place. Okay? So what I'm going to do now is go back to my Lagrangian and now write it as h bar c psi bar gamma mu d mu psi plus mc squared psi bar psi, which we can of course expand with the definition of this covariant derivative to the original term plus a new term I q h bar c psi bar gamma mu a mu psi plus mc squared psi bar psi. Okay. To get to here, I just used the definition of that new derivative. And now what I want to do is I want to transform this. Okay? Yes?
Why are we allowed to do that?
I'm the boss. Because I'm the boss and I said it's okay. It's okay. You can dip the chocolate in the peanut butter. I said, okay. I'm not breaking any rules. Why can you do it? You can't. Hold on. You can't do that and say that you have the same theory. We're creating a new theory. So I'm not trying to argue that I'm doing something and in the end it's just going to be the same thing I started with. I'm genuinely going to get something new out of this. It's going to be new and very interesting. But all I want you to realize is that the particular choice that I'm making is motivated simply by wanting this to be able to work when phi is a function instead of a constant. I still haven't shown you how it's going to make that work. That's the next step. Okay? But another reason why I can do this is because I know what this is going to end up with, and it's going to be something that plays a very important part in your life. Okay? And it's not people's significant others. Here we go. All right. So we transform everything in sight. Okay? In particular, we know how psi bar transforms. Gamma mu. Actually, I'm going to work with this expression because it's more explicit. D mu e to the I q phi x nu psi. And then in this expression, I'm going to have, of course, psi bar, e to the I q phi x nu, gamma mu. I don't yet know how A transforms. It's a field, but I don't know how it transforms, so I'm just going to actually just call that A prime mu. And I'm just going to go ahead and leave this last term as mc squared psi bar psi, because we already know that last term is invariant. Okay? So all I did was I took this new Lagrangian in this kind of broken down form and transformed everything. This is the same thing I did in the previous case. The new term, I'm writing down the transformation of everything, except I don't yet know how A transforms, so I'm just going to call it A prime. Okay? And then what we're going to find is the following expression after we kind of massage the crap out of this. So, yeah, here we go. So doing the similar steps that I did before, using the product rule to distribute this derivative, and then I'll get two terms, and then I can cancel the exponentials in both those terms, and then collecting everything, this is going to simplify to the following form: h bar psi, h bar c, psi bar gamma mu, d mu psi. So again, I get that original term that I started with, which we might have expected. I'm going to get a new contribution, or sorry, this is the term that was screwing me up last time. Okay, so that's the term which, damn this term, damn this term. This is the term that screwed us up last time. But now, of course, I get a new contribution from this guy, and that's going to take the form IQ h bar c psi bar gamma mu a mu prime. This is just, I'm just canceling the e's here, and then writing what's left. MC squared psi bar psi. Okay. There's a little bit of work to go from here to here, but it's really what I did in the previous case, except you just have this new term, which pops up down here. Right? And let me make sure I'm not missing, yeah, missing factor of, oh, that is a C. It looked so unlike a C that I didn't recognize it as a C. So now we start seeing something that is highly suggestive. This term and this term have a lot of the same ingredients, right? It's got the IQ, h bar c, the psi bar, the gamma mu, the psi. So if you just squint and focus on that and that, then you can probably determine after a few moments thought that if the transformation of a mu takes the following form, then my Lagrangian is invariant. Because if I plug this expression in for A prime here, this piece is going to exactly kill off this term. I'm still going to be left with this guy, but that's okay because that's what I started with. You guys okay with that?
Sure.
You see the symmetry that I'm talking about? I started with a Lagrangian. I did this local transformation. And as long as A behaves in the correct way, I end up with the same Lagrangian at the end. Okay? You ready? I started with psi. I found myself having to introduce a mu, but in the process, I discovered that term right there. What is that? That's an interaction. That is a product of the psi fields and the a mu field. So this term is an interaction. So I started with non-interacting spin-a-half particles, the psi's and the psi bars. I started with a global symmetry. To make it a local symmetry, I was forced to not only introduce a new field A, but also an interaction between psi and A. Okay? Now, at this point, the field A in my Lagrangian cannot propagate. What that means is if you tried to apply an action principle to get an equation of motion for A, you wouldn't get a very interesting result. At this point, all you could do is just say A mu has this form, and then you just do the physics that this Lagrangian corresponds to, given the functional form of A mu. But what we would like to do is have an equation of motion for A mu that's useful. So if we want to allow A mu to propagate, if we want to get useful equations of motion for it, what we need to do is give it a kinetic term. Well, going back to our free kinetic terms, which kinetic term do you think is going to be appropriate for the field A mu? It's probably the one that involves A mu. Yeah. So it turns out that A mu is a vector field. It's actually a dual vector field, but you can always raise the index and make it into a vector field if you like. And so once we identify that it's a vector field, we immediately know which type of kinetic term to give it. Okay? So our Lagrangian would then become, and we can now write this a little more compactly, h bar c psi bar gamma mu d mu psi plus mc squared psi bar psi plus 1 over 16 pi f mu nu plus 1 over 8 pi mc over h bar squared a mu. Okay? However, and this is going to be a very, very important observation for when we eventually talk about the Higgs mechanism, unfortunately, that Lagrangian is not invariant under this transformation. Clearly, the first two terms are. We kind of constructed it so that these two are. It's what we've added. It's the kinetic term. Okay? So let's explore the kinetic term for a moment, and then we'll sort of get the final punchline to this story. So there are two pieces to the kinetic term. There's the f mu nu and the f mu nu. So we'll start with the f mu nu. Remember that secretly this is eta mu lambda, eta nu beta, d lambda a beta minus d beta a lambda, d mu a nu minus d mu a mu. Okay? And you worked with that in your homework. And now what we can do is we can say, okay, every A goes, if I transform this, goes to A mu minus D mu phi. Okay? That's the transformation here. So if I do that, what I find is that the new form of this term, which I'm just going to call the primed form, is given by this expression. And now everywhere I see an A, I replace it by this new A. And so I'm going to have d lambda A mu minus D mu phi minus d beta A lambda minus D, sorry, these should be betas, d lambda phi d mu A nu minus d mu phi minus d mu A mu minus d mu phi. Okay? Now that looks complicated, but watch. Here's the magic. Are you ready? If you FOIL all this crap out, you're going to get the terms you started with. That's the d lambda A beta, the d beta A lambda. The new terms are going to be d lambda d beta phi, d beta d lambda phi with opposite signs. But what's the difference in those terms? It's the order in which the partial derivatives are acting. Here you have d lambda d beta, here you have d beta d lambda. But what do we know about partial derivatives? They commute. So this term will be minus d lambda d beta, this term will be plus d beta d lambda. Those are going to cancel. And in fact, the same thing is going to happen between these terms. So all I'm going to be left with at the end of the day is exactly the expression I started with. Spencer.
What kind of consideration does it call where there's this stuff in it? It's like some nasty, twisted field. Gross.
Come to Physics X tomorrow. We'll talk about it. Okay, anyway. All right, so the FB new term works out. So I'm just going to go ahead and get rid of that. That's all sweet. And so what must be the problem is this guy. And so let's just look. The constants don't matter. Constants are not going to screw up any invariance. So really we just want to focus on a mu, which of course is just eta mu nu, a mu. And so now if I transform this is going to become eta mu nu, a nu minus d nu phi, a mu minus d nu phi. And there is no way that that is going to return what I started with. Okay. We don't have any fancy cancellation between switching the orders of partials. Okay. So unfortunately, this story plays out so nicely, except that we're not allowed to put this term in the Lagrangian. So what can we conclude? Yeah, the field we have to add needs to be massless. Because if it's massless, this term is 0. Okay? So therefore, the mass of this new field needs to be 0. Now that's an incredibly important observation because later on we'll discover that when we look at the real world, we see massive gauge fields. And it's going to be very tricky to figure out how you can have massive gauge fields without screwing this up. And that is, of course, where the Higgs miracle is going to come into play. Okay? But for now, without resorting to something fancy, we added a new field A, we allowed it to propagate, but in order for us to maintain this local symmetry, this new field A has to be massless. But otherwise, if I erase this guy, then I have this nice property that L goes to L prime, which is just exactly the same L I started with. Okay. Okay, so let's get rid of all this garbage. Step 4. Here we can pretend. You know, it's like church. And you're like, is it wine? Is it not wine? No, it's grape juice. It's just grape juice. Okay, all right. So no, really, like I have just done all this like nasty, you know, make the symmetry apply and make it local and introduce this crap. But really and truthfully, let's talk about what we have. Okay. So our Lagrangian, which is just so wonderful, I don't mind writing it like a gazillion times. It's just so nice. And remember, you can have a mass for the psi. That's fine. It was the mass of the new field A that was screwing everything up. Our Lagrangian is invariant under a transformation which takes the form e to the I q phi. Okay? This is a complex number, but it is a complex number of unit magnitude. So there is a certain sense in which you can imagine that this thing just corresponds to shifts along the position of the unit circle in the complex plane. If I took the full set of these, phi can range from 0 to 2 pi, I'm actually describing a group that we have seen before, and it is called U1. Because if you think about it, a matrix of that form, or a one-dimensional complex matrix of that form, satisfies the unitary property, trivially. Okay? And of course it's U1, it's a one-dimensional, it has a one-dimensional matrix representation, a complex number. Okay? So what we've discovered is that this theory is really a theory of local U1 invariance. And it has a name. What do we call it? Anybody ever seen this theory before? I'd say it's important to your life. It goes by many names. My favorite is electromagnetism. So everything that I have done constitutes classical electromagnetism. This piece right here, if you take the Lagrangian and bury the action associated with it, and then find the equation of motion for A, this piece right here is going to flesh out Maxwell's equations. These terms here are going to flesh out not only the Dirac equation, but also there's going to be an interaction, because remember this capital D has a mu in it, and it's going to include the analog of the Lorentz force law as it applies to spinors. This Lagrangian is the starting point if you want to quantize the theory for doing quantum electrodynamics, which we will of course study in more detail. But this is it. The punchline of this is that electromagnetism, and more importantly, the form of the electromagnetic Lagrangian, is completely determined by this recipe. Now that might not seem familiar to you, like you studied electromagnetism in Physics 200, you looked at E fields and B fields and charge particles, and you let the charge particles move and you got B fields, and you looked at Ampere's law and Gauss's law and all this crazy stuff. And you might have loved it in that form, and you might have seen it in this form, and you might have hated it in this form, okay? But here's the reason why this form is so useful. When you think about electromagnetism in terms of charges and moving charges and E fields and B fields, there is zero connection between that and the weak nuclear force, the strong nuclear force, or gravity for that matter. However, if you allow yourself to consider electromagnetism in terms of this recipe, this is the exact same recipe that you would follow to create the weak nuclear force, the strong nuclear force, and in fact gravity. Okay? So it's this approach of thinking of the forces as gauge theories that actually lets us sort of unify how we think of all interactions in nature. Okay? And of course, in all of this, I should add that once you actually recognize this is electromagnetism, this guy Q then gets a physical interpretation. It's just the electric charge. Hence the suggestive name. Okay?
Alex?
Yeah.
So to get the strong force or weak force out of the same recipe, do you just change your when you find the covariant derivative, do we just change that definition to get the different theories out of it, or where do we?
Well, we're going to do that in detail next time.
Okay.
And what's going to happen is you have to, so the Dirac Dirac-Lagrangian actually already had the global symmetry that you can work with to get electromagnetism. That's something kind of unique about electromagnetism. To get the strong interaction and the weak interaction, you actually have to take the Lagrangian and interpret the psi a little bit differently. In particular, if you interpret psi as not just a spinner in space-time, but a two-component vector in an internal complex vector space, then there's a new transformation you can do that's affected by 2x2 matrices. And if you follow this story in that case, you'll generate the weak interactions. If you instead think of psi as a three-component vector in an internal vector space, then your transformation will be affected by 3x3 matrices, and that will end up giving the strong interactions. And we'll see the details of that. It's going to be slightly more complicated because of the fact that this is an abelian group, and those other two cases are non-abelian. And I'm going to talk a little bit about that now, actually. Matt?
I'm just curious, is the 2x2 for the weak interaction the psi plus and the psi minus we talked about last time? For time study or no?
No. Those are all those components of the Dirac spinner are components as they pertain to transformations in space-time. These transformations are not transformations in space-time. They're space-time dependent transformations, but they're transformations of the fields. One way to remember that is that these transformations do not affect the gammas or the d mu's, but a transformation in space-time would affect those. All right, so I'm not going to go beyond this example today. We'll talk about the other cases next time, but what I am going to do is kind of show you a nicer way to think about this, because when we turn to the non-abelian case, it could get really, really hairy unless you kind of organize things in an appropriate way. So let me actually show you one way to think about what we're doing. So our original starting point, psi bar, gamma mu, d mu psi. So this failed. And when I write these phi's now, these phi's are functions of where you are. I'm just not going to write the coordinate dependence in the interest of time. Let me write it this way. So the failure is exactly this observation that you cannot just move this transformation past the derivative. If you could, then it would have been invariant. Okay, but we couldn't, and that's where it failed. One way to think about how we fixed it is the following observation. We ended up having to use a new derivative, but if you keep it in terms of the new derivative, instead of breaking it apart like I did, if you keep it in terms of the new derivative, then you find the following. So the whole point of this new derivative in this notation is that this piece can in fact be moved past the capital D mu, where it couldn't be moved past the original D mu. You can go back into the details that I had up on the board previously to actually see that that's the magic that happens. Okay? So one way to think about this is that the transformation of the derivative of a spinner, which would be d mu prime e to the iq phi, and that's a d prime. Because remember, d mu contains not just little d mu, but a, and that a transforms. Okay, so actually the observation is that I can take d mu prime e to the iq phi, and this I did demonstrate is equivalent to that. E to the IQ phi times the original d mu. And so what we're essentially arguing is that this thing transforms like this. That is, the transformation of this just gets an overall factor. We could not say that for this. That's just not true. But if we work in terms of the capital D, it is true. Okay? Now, if you took general relativity, this idea should be familiar. In general relativity, what we discovered is that if you take an ordinary derivative of some vector field or higher tensor field, if you did a coordinate transformation on this, it did not transform like a tensor. That is, this does not transform with the appropriate transformation rule that you would expect of this tensor. However, what we did in general relativity was we took the ordinary derivative and we replaced it by a new thing called the covariant derivative. And the covariant derivative was constructed precisely so that this obeyed the tensor transformation law. So for those who haven't taken general relativity, it's okay. This should not be familiar. But what I will tell you is if you take general relativity, we're going to repeat everything we just did. It's going to look a little bit different because in general relativity, the transformations you're working with are actually space-time transformations. These transformations are not space-time transformations. They're internal field transformations. However, the analogous story in general relativity is that you're localizing space-time transformations like Lorentz transformations and rotations. But of course, localizing those transformations creates an interaction, and what do we call the interaction?
Gravity.
Gravity. Okay. So gravitation comes out from a similar argument. Okay. Now, one final observation is that we, in working this out for electromagnetism, things were actually a little bit simpler than they should be, or than they're going to be in general because of this Abelian nature of the gauge transformation. U1, any two U1 transformations commute with each other. It's Abelian. So what we want to do is we want to see if there's a way that we can generalize this so that it'll be a natural extension to when we get to the non-Abelian case. So in particular, what we're going to discover is that this term, which is gauge invariant for the Abelian case we just did, this term is not gauge invariant for non-Abelian cases, which we're going to study next time. So what I just want to give you right now is a preview of how you would generalize this to an arbitrary transformation, and we'll see that it reduces to this. So one way of actually figuring out what the form of this should be is to take two covariant derivatives and form their commutator. And let me show you that this reproduces this. Okay? So for this case, we know what the covariant derivatives are. Okay, the commutator, of course, is just a commutator. I do them in one order and then I reverse doing them in the other order. And then the only thing you have to be really wary of is that this is a derivative, so it acts on everything to the right. So there's no sense in which you could just take this term, take these terms, and swap them and just say this is zero. Because you actually have to pay attention to the fact that this derivative acts on everything, and so too does this derivative. Okay? So if you expand the crap out of this, then you'll find an expression like this. And this is, again, just by distributing that derivative. You're going to have product rules because this d nu is going to act on the product of a nu and psi. So you've got to distribute that using the product rule as you're familiar. And in the end, you're going to get an expression like this. Sorry, I missed a term up here. Okay. So you could all do this. I mean, this is just multiplying these out and then acting with the derivatives, expanding everything using a product rule. And then, lo and behold, we see a lot of nice cancellations. Where is it? There it is. Yeah. Okay. Oh, sorry. Yeah, that's what I'm confused about. That's a d nu. And
What's the last one? Isn't it?
yeah, there it is. There it is. I couldn't see it because I wasn't willing to look that far down the board. There you go. Okay. So at the end of the day, we've just got IQ, d mu, a nu, minus d nu, a nu, psi. And so now what we can do is we can define f mu nu, which is this combination right here, as minus the commutator of d nu over q. Okay. And what I would argue is that instead of trying to write this down, which we're not sure if it will be gauge invariant, if we actually work with this expression, which gives us the same thing in this case, this expression in more general cases will be gauge invariant, okay, even if it's a non-abelian transformation. Okay, so this is really the way we're going to write down our f mu nus, and then once we write them down, we again use the same Lagrangian term. Okay. Now, for some of you in the room, this expression should be familiar. Does anyone remember that?
It's Christoffel.
Actually, no. What is this?
The Riemann.
This is the Riemann curvature tensor. We derived the Riemann curvature tensor in general relativity by looking at the commutator of the covariant derivatives in general relativity. So there is a direct sense in which the Riemann curvature tensor in general relativity is analogous to the electromagnetic field strength tensor in electromagnetism. So the f mu nu you've probably seen if you've looked at electromagnetism covariantly. In gravitation is replaced by this crazy 4-index object called the Riemann curvature tensor. Okay. And if you wanted to flesh out the analogy, remember that this covariant derivative in general relativity is the ordinary derivative plus Christoffel symbols, where now you can see that the Christoffel symbols sort of play the role of the new gauge field. Okay. Any questions? I don't know how we started 5 minutes late and ended 5 minutes early, but we did.
So we,
Hold on.
I mean, I can ask you after, it doesn't
Well,
really.
you can ask me now.
So when we did NGR, when we worked with the Christoffel symbols, we went through problems like showing how that's the same as writing like the gradient in cylindrical. and stuff.
Sure.
Is it the fact that cylindrical coordinates are like spatial, that covariant derivative definition works for so many things, where, you know, the one we just found for
Well, what we were
electromagnetism is
doing,
weird?
what we were doing in general relativity when we wrote this derivative was we were writing a derivative whose form was invariant under changes of coordinate systems. That is, it transforms like a tensor when it acts on something. When you pick a coordinate system and you actually write down the Christoffel symbols, you get all of these expressions you saw in electromagnetism and you hated, you know, what does the divergence look like in spherical polar coordinates? What does it look like in cylindrical coordinates? Those are really nothing but these Christoffel symbols. We didn't call them that when you studied electromagnetism because we didn't want to wound you. Okay? But yeah, so the idea is that even though it looks different in specific coordinate systems, this quantity acting on a tensor altogether behaves like a tensor. I don't think I actually answered your question.
No, that
so I
makes
just
sense.
repeated the observation.
So like that's the gauge freedom in GR is coordinate transformations, right?
Sure. Yeah, exactly. The gauge freedom in GR is local coordinate transformations.
Right.
And so when we were constructing tensors, we were saying, I want everything to transform as a tensor. That is, under coordinate transformations as a tensor.
Mm-hmm.
Here, though, the transformations that we're going to be studying in this class are all going to be transformations in an internal space. Now, don't get me wrong. There is a way that you can geometrize all of this. And you can take these internal spaces and actually consider them as part of a hybrid space-time. And that's a program called fiber bundles. And then there's a very nice geometrization of this. And there's a lot of interesting topological analyses that you can do with those sorts of constructions. But we're not going to touch on them in this course. Okay, so next time we get together, what we're going to do is essentially generalize this to the non-abelian cases. And in the process, we're going to write down the Lagrangians that will underlie the weak interactions and the strong interactions. Okay? And then we're going to turn to this thorny problem of, we know at least from observation that the weak interaction bosons have mass. So if we can't have this term because of gauge invariance, how do they get mass? And that's where we'll find ourselves talking about the Higgs mechanism. Okay. Other questions? All right, so you got a pretty decent sized homework assignment that is due on Tuesday, and I will be adding one more problem to it. And I'll add that tonight. And it'll be based on what you worked on. That's why I got it so quick. I didn't have any more questions.
I mean, you had a pretty weekend until assignment 7.
Just give me that look, Spencer.
No, actually,
Oh, yeah,
assignment 7
you decided.
Yeah,